Good day everyone, so today we'll be talking about PN junctions at equilibrium. So for the past few lectures, we've been dealing with semiconductors that are homogeneous in their electrical properties. But these kinds of semiconductors have very limited applications in our devices. Where we actually use our semiconductors is in our non-homogeneous semiconductor structures. These are way more important in our devices. Most of these structures involve this kind of feature, our PN junction, where a P-type and an N-type semiconductor are put into contact. So in this video, we'll be describing how this PN junction behaves in equilibrium. So we'll be creating a model for these PN junctions, and we'll be describing the properties of the ideal PN junction at equilibrium. So the ideal PN junction, this is also known as your abrupt or your step junction. It acts as an ideal diode, only allowing the current to flow in one direction. So for those who don't know, this is your diode. A diode is a circuit element which can behave either as an open or a closed switch. So pag open switch siya, this does not allow current. Meanwhile, pag closed switch siya, this allows current to flow. So depending on the polarity in which we apply our voltage across this diode, mag-act siya as either an open or a closed switch. So now going away from the electronic description, and now let's go to the semiconductor description. Let us consider the PN junction na ito. Assume that this PN junction is composed of two regions in contact, the P-type region and the N-type region. The P-type region, so let's redraw it here. Let's go down. This is your P-type, and this is your N-type. We assume if this is your X scale, at the junction center, this is 0, X equals 0. Your P-type junction is at the region X is less than 0 with concentration of acceptors Na. Meanwhile, yung N-type region natin, this is at the region X is greater than 0 with with donor concentration Nd. We will also assume that this PN junction is a homojunction, or the P-type and N-type regions are of the same material. At regions far from the junction area, for the P-type, the equilibrium hole and electron concentrations would be denoted by PP and NP respectively. So this is holes, this is your electrons. Meanwhile, for the N-type region, you can also use the same notation, Pn and Nn respectively for your holes and electrons. From the mass action law, we know that for a semiconductor material at a given temperature, this holds true as long as we have a non-degenerate semiconductor. So Ni squared is equal to Np, and since the P-type region and the N-type region here are the same material, we can then say that Pn Nn is equal to Pp Np, or the concentration of electrons and holes, yung product nila, at the N-type region would be equal to the concentration of holes times electrons in the P-type region. For, tawag dito. For semiconductors at, let's say, the room temperature, if we assume that all of our donors and our acceptors are ionized, we will then get, for the p-type semiconductor, Pp is equal to Na, and then Np, or the concentration of holes in the p-type, would be equal to Ni squared over yung Pp natin, which is Na. Meanwhile, so this is for p-type region. For the n-type region, you would get that the concentration of your electrons in the n-type region will be equal to the number of donor atoms. Meanwhile, yung Pn natin from the mass action law will be equal to Ni squared over Nd. Bringing a p-type and an n-type semiconductor into contact, as shown here, p-type and n-type semiconductor would lead to the recombination of majority charge carriers. So, majority charge carriers natin is in dominant charge carrier for each of these regions. So, for P, it is your holes, and for your n-type, it is your electrons. So, the recombination of these charge carriers will be brought about by the diffusion of your holes to one side and your electrons to the other side. Since yung holes mo mas marami in the p-type region than the n-type region, it would go to the lower concentration. Same with the electrons, it would go to the lower concentration, which is your p-type region. If your holes and electrons would meet, they would recombine. The recombination of these two, again, hole mo is something like this. Your hole is a vacancy, or not a vacancy, it's an electron state not filled by an electron in the valence band, and yung electron mo is a free electron in the conduction band. If they meet, they would essentially annihilate, mawawala yung ating free charge carrier. So the diffusion of these charge carriers would lead to the recombination of the holes and their electrons. So they would essentially cancel out, and this would leave uncompensated acceptors at the p-type region and uncompensated donors in the n-type region. So these uncompensated acceptors, since holes yung give up nila, tanggal ka ng holes sa kanila, which is positive, this will be negatively charged. Meanwhile, for your uncompensated donors, since electrons yung give off nila, this should be positively charged. So do recall that even though p-type and n-type semiconductors have an imbalance between your electrons and your holes, electrically neutral pa rin siya as a whole, as a buo, not a whole na yung charge carrier. As a whole, and yan. So, pag nagtanggal ka ng hole, ang matitira sa'yo is negative charge kasi hole is positively charged, and for your electrons, pag nagtanggal ka ng electrons, matitira sa'yo positively charged particles. So, these uncompensated acceptors and donors would lead to regions of negative charges at the p-type region near the junction and positive charges in the n-type region near our junctions. So do take note though that these charges here, they won't move. Why will they not move? They will not move because yung negative charges mo and positive charges mo, these are actually caused by your dopant atoms. And your dopants are integrated into the crystal structure. They are chemically bonded there. hindi yan basta-basta gagalaw unless i-break natin yung bonds. But we don't have enough energy in normal operation to do that. So they're just static there, mobile there. So due to the production of charges at opposite sides of this junction, meron kang negative dito and positive dito, will actually form an electric field. Yes. We'll be forming an electric field due to this one. We call this your built-in electric field. And the presence of this electric field then would then cause the drift of the minority charge carriers. So this electric field would cause the drift of minority charge carriers. So the minority carriers are the carriers with less concentration in our different types of semiconductors. So dito, yung negative mo, yung sa p-type, the minority charge carrier is your electron. And for the n-type, yung minority charge carrier mo is your holes. So due to this electric field, pupunta siya, mag-drift siya. Ganun siya. Shook. And shook. Punta siya sa opposite sides. At equilibrium, the current due to diffusion and drift, J diffusion plus J drift, should be equal to 0. Kasi dapat wala tayong net movement of charges. And at equilibrium 2, so again, look at this. At equilibrium, yung width nito, due to this one, since nag-equilibrate na yung diffusion and drift currents natin, magkakaroon tayo ng point in such yung width netong depletion region natin. You can define this as W0. This would be the width of your depletion region. Ito yung depletion width natin. This depletion width, this is the width of our space charge region at equilibrium. To simplify our model for the ideal PN junction, we can invoke the depletion approximation. Depletion approximation. In this approximation, we assume that there is an abrupt transition between the quasi-neutral region, or the bulk P-type and bulk N-type regions, to our depletion region. Specifically, we mean by that is that outside of the space charge region, the semiconductor is neutral with no charge depletion. Meanwhile, inside the space charge region, we will see our negative and positive charges. Dun lang siya concentrated, and that all of our charge carriers have, or all of our majority charge carriers have recombined. So if you graph that in this Q versus X, Q is your charge concentration, and X is yung ating position, where X equals 0 is yung ating junction here. Your charges would all be contained within our depletion region. For the P-type region, so this P-type, this N-type. For the P-type region, yung ating charges would be negative. Meanwhile, sa N-type region, ang charges natin would be positive. Yung extents nitong charges natin would be in W0, and we can define two x's here. We can define yung ating x P0 and x N0, which will serve as the extents of our depletion region in the P-type and N-type regions, respectively. Outside of the space charge region, we can assume that the semiconductor is electrically neutral with no charge depletion, and that the concentration of holes and electrons would just be the same as the bulk p-type and n-type regions. Then, by using the depletion approximation, we can assume that there are no free holes or electrons inside the space charge region again. And since the entire PN junction, or our entire semiconductor, needs to be electrically neutral, the space charge region must also be neutral as a whole. Or this one, itong buo, dapat equal yung charges natin dyan. The charges here should be equal to the charges here. Expressing this mathematically, we will get QA NA XP naught would be equal to QA ND X N naught, where Q is the elementally charge, A is the cross-sectional area of our junction, XP naught and XN naught are the extents of our depletion region at the P-type and N-type semiconductors respectively, and NA and ND are the concentrations of acceptors and donors at our semiconductor. At our semiconductors na P-type and N-type respectively. So since your depletion rate, W naught, can be expressed as XP naught plus XN naught, combining this one with this expression, so dito maka-cancel yung Q and A, cancel si Q and si A. Combining these two, we will get that XP naught would be equal to ND over NA plus ND W naught, while yung XN naught natin would be equal to NA times NA plus ND W naught. So we can see here that the space charge region would extend more depending on the yung ating space charge region, the extent of the space charge region depends on the dopant concentration. So if we increase the donor concentration, we will see that it would actually extend more into the P-type region. So pag mas concentrated si donors sa N-type region mo, your depletion region would extend more into the P-type region, and vice versa. If we increase the concentration of acceptors in the P-type region, mag-i-increase naman yung extent ng ating depletion region into the N-type semiconductor. From the charge profile of our PN junction, we can actually get your built-in electric field. So using Gauss law, ito, D of EX is equal to DX equal to QX over epsilon, where QX is the charge profile of our semiconductor material and epsilon is its permittivity. For either side of the junction, so for the P-type side, we'll have this expression, DEX over DX is equal to negative Q and A. This is yung charge over epsilon. This is the charge concentration. For epsilon, this is from negative X P naught to 0. For the N-type side, DEX over DX will be equal to Q and D over epsilon. This is from 0 to X and naught. From these relations, we can see that the electric field strength varies linearly on either side of the junction. Since this is just a constant value, dx over dx is just yung slope, linear yung slope mo for the P-type and N-type regions. We can integrate these two expressions and we can use boundary condition para makuha natin yung ating expression for electric field. At the boundaries of our charge carrier or our space charge region or depletion region, yung electric field must be equal to 0. So this will mean E is equal to negative x p naught. E negative x p naught should be equal to E x n naught. And at the boundaries of our space charge region, your electric field should be equal to 0. We would get, integrating this using this boundary condition here, E of x would be equal to negative q n a over epsilon. So this is for the p-type region. X plus x p naught. This is from negative x p naught less than x less than 0, or from negative x p naught to 0. Meanwhile, for your n-type region, we would have q and d epsilon be equal to x minus x n naught 0 to x n naught. The built-in electric field strength profile using this expression here, if we graph this, we will see would look something like ganito. E, x, and x. Again, x at 0 is our junction. Ito yung position ng junction mo. This is x p naught. And this is x n naught. It looks something like this. Linear and linear. And we will see that your electric field is at a maximum at our junction. X equals 0. So due to our built-in electric field, there must also exist a built-in potential, Vx. Yung built-in potential natin from the electric field can be derived from this expression. Ex is equal to negative d v x over dx. Meron na tayong expressions ni ex dito and dito. We can solve for vx by integrating this expression. So integrating this one with respect to x, we get vx, and we get vx is equal to q and a over epsilon x squared over 2 plus xp naught x. This is from negative x p naught less than x less than 0. So this is for the p-type region. For the n-type region, we have vx equal to q and d over epsilon x squared over 2 minus x and not x. This is from 0 to x and not. By letting the potential at x equals 0 be equal to 0, or at x equals 0, our potential is equal to 0, we would get this graph. We have potential here, and we have x here. At x equals 0, potential is equal to 0. At the extents, or outside the space charge region, we can assume that the potential is constant since there is no charges naman, or there is no changes in the charges. So parang ganito siya, and ganito siya. And along the space charge region, it would vary with our change, and your potential profile would look something like this one. So this is your xp naught negative, and ito yung extents ng ating depletion region, xn naught. And yung v natin, from our expressions dito, we would have q and d over 2 epsilon times xn naught squared. Meanwhile, sa kabila, this one would be equal to negative q and a over 2 epsilon times x p naught squared. The total potential difference across this junction itong junction na to and ito, or across taas this junction here. Yeah, so long. The potential difference between this one will just be equal to the subtraction, or yung potential dito minus potential dito. Or V naught, the built-in potential, will then be equal to V x and naught minus V negative x V naught. So equal to Q and D over 2 epsilon x and naught squared minus negative Q and A 2 epsilon x V naught squared. Or we'll get V naught is equal to Q and D over 2 epsilon x and naught squared plus Q and A over 2 epsilon x V naught squared. We can manipulate this one using our expression for the depletion width. We will get V naught is equal to Q over 2 epsilon and A and D over NA plus ND W naught squared. We can also get another independent expression for the built-in potential by using the expression for our drift and diffusion currents. We know that drift plus diffusion currents at equilibrium, this should be equal to 0. Upon derivation that we will not cover here, just try to read the modules, we would get that your built-in potential can be expressed as V naught is equal to KBT over Q ln BP over PN is equal to KBT over Q ln of NN over NP. So nakita natin dito your built-in potential will be a function of the number of holes in your p-type over the number of holes in your n-type, or the number of electrons in your n-type over the number of electrons in your p-type region. You can also express this expression here as a function of yung ratio between the majority holes and the minority holes, like this one, PP over PN equal to NN over NP, and we'll just be making this an exponential expression, exponential of Q V naught over KBT. Then, for this expression, we know that PP and PN, from dun sa way back, kanina pa natin ito discuss, yung PP natin is the number of holes in your p-type semiconductor, and the PN is the number of holes in your n-type semiconductor. We know that PP is equal to NA, and PN, the minority charge carriers natin, is equal to Ni squared over ND. You can get V naught is equal to KBT over Q times ln of NA ND over Ni squared. From our expressions of V naught, yung dalawa, we have V naught as a function of your depletion width, omega naught, W naught squared, and we have V naught as a function of yung concentrations Na, Nd, Ni squared. From these expressions, we can then get an expression for our depletion width. So combining both of them, we have, so first we manipulate this one, we isolate the W naught at one side. We will get W naught is equal to square root of 2 epsilon over Q Na plus Nd over Na Nd V naught. But we have an expression for V naught here. V naught is equal to KBTQ over Ln NaND Ni squared. And putting this here, we will get W naught is equal to this one part of 2 epsilon KBT over Q squared Na plus Nd over Na Nd Ln of Na Nd over Ni squared. So why do we want this expression? Maganda tong expression na to since we can get or we can calculate for the width of our depletion region just from yung concentration ng ating acceptors, concentration ng donors, the temperature, the permittivity of our semiconductor, and the intrinsic charge carrier concentration. So basically all constants that we can control or we know from our process. And this helps in the design since usually we want our features in our, let's say in a CPU or in a transistor, we want depletion width not to extend more than the actual width of our system. Then the extent of our depletion width into the PN junction can also be determined. We know that W naught is equal to XP naught plus XN naught. So XP naught be equal to square root of 2 epsilon over Q NB over Na plus ND V naught. So just input V naught there, and XN naught will be equal to square root of 2 epsilon Q Na over ND Na plus ND V naught. So due to the presence of the built-in potential, our energy bands, especially the conduction and the valence band of the p-type and the n-type semiconductors, will get shifted in a phenomena that we call band bending. So band bending stems from the fact that in thermal equilibrium, the Fermi energy throughout a material should be equal at all parts. So let's say we have a p-type and an n-type semiconductor. Their Fermi energies are yung dash lines natin dito. So this is the Fermi energy for the p-type and the Fermi energy for the n-type. In thermal equilibrium, these two must be in a dito. Dapat pareho silang dalawa. So to accommodate this, so for these two Fermi energies to be at the same level, what would happen upon contact is that the p-type and the n-type, the band structures of p-type and the n-type, what would happen is that they would align their Fermi energies. Kinda like this one. Yes, nag-align siya. And this would cause, if we look at this one, magkakaroon tayo ng band bending dito sa ating band structure because we align yung Fermi energy natin na EF for the p-type and the n-type. And this amount of band bending here is actually equal to negative QV naught. Or equal siya dun sa ating elementary charge times yung ating built-in potential. So again, this band bending arises from the need for our Fermi energy to be equal. So, itong phenomena to, this will be more elucidated. Yes, big word, elucidated in the next module. These are non-equilibrium properties. But it's a property of materials in thermal equilibrium that the Fermi energy should be constant in all areas para wala tayong net movement of our charge carriers or our electrons. And this band bending here, this is equal to Q times yung ating built-in potential. This is the amount of our band bending. So I know that this module has been very long, or this video has been very long, so I'll stop here and I'll see you all in the next one. Thank you!